Hello physics. We're about to start our lab on composition of concurrent forces, vectors. And we're going to use this little force table to do our lab. So this is going to be our data table, and we're going to do 3 different trials. And one of the trials we're going to do with our forces going all 120 degrees from each other. Just want to introduce you to the force table. It's got 3 legs because with 3 legs you always define a plane. You remember that from geometry. And these wheels here are free to rotate. I can move this around, and this little screw here is to keep me from having it all fall off. If I take off a weight, it just catches it for me until I put it back on. So we're going to look at this ring here, and I will show you from a elevated viewpoint what it's going to look like. We're going to put weights on here to balance it, and you can see that this force has got to be balanced by these 2 forces. So let's get started. So here we have a nice example of a lab write-up that was started. Includes a little sketch of our apparatus, some equations and so forth. And so this will be a good way to start your lab. The next pages are going to be made up of the data table, which we're going to just fill it out on our sheet here, and then later on transfer it to our data table here. Now, don't use this data. This is data that some other student did. We're going to do something similar, but I just wanted to show you about what the drawings look like. Now, I really recommend that you make a full page for this drawing and the next 2 drawings, that you use a full page. You've got plenty of space, make your vectors big, and then show your calculations. So you have to have your drawing, you're going to show your scale, you're going to show your calculations for the law of cosines and law of sines. And we'll talk a lot more about that, but this is the basics of what it should look like. So for the first part of our lab, the instructions tell us to place all 3 of these wheels at 120 degrees to each other. So here we have 0, we go to 120, we go to 240. So they're all going equal and opposite directions. So we should be able to put equal masses on there. So you can see here I've got 100-gram masses on each wheel here. So there's 100 grams on each. And while force is measured in newtons, we should have to take 0.1 grams times 9.8 to figure out how many newtons. Since the ratio is going to be the same, we're going to get a little bit lazy on this, and we're just going to use grams. So for our first trial, trial 1, our force, the magnitude of our force is 100. Now what's the direction? We can decide any which ones. It doesn't matter which one's force 1 or force 2, but we can choose force 1 to be at 0 degrees. Then we can take our force 2, and we can say, well, that's also going to be 100. And it is also going to be at 120 degrees. And then our equilibriant, the one that's matching these 2 vectors, that one is going to be 100 grams also. And the degrees will be 240 degrees. All right? So then your lab goes into some instructions, and here is a diagram showing you basically what it looks like. Okay, so now we're going to start our second trial. We'll talk about what to do here once we get the other 2 trials done. But we're going to start getting our data for trial 2 and trial 3, and then we'll talk about the rest. So we still have it set up for trial 1. And what we're going to do, just to illustrate this, is we're going to move this to 140. And we're going to move this one to 220. So we're just going to move them equally. So you see now we've shifted the weights over this way, and it's pulling more this way. And so this resultant is not enough to keep it in place, and that's why we have this screw here. So I'm going to add some masses to this one here to try to pull it this way. So I'm going to start by adding a little bigger weight So we have 100 on there. I'm going to add a 50. It pulls a little bit, but not enough. And so I've got another 20 here. Let's see what 20 does. Well, 20 is too much. Take that off. How about a 10? Let's try 10. Well, that's kind of close, but still a little bit too much. So let's try a 5. This is a 5. Wow, that's really close. Now, I have to adjust this a little bit so that it matches the angle. And you'll see that 5 is a little bit too much. So I've got some 2s here and a 1. Let's see. Let's put 2 2s on there. Wow. I'd say we're pretty close. All right, so we can write down our directions are 0, 140, and 220. And just to keep it simple, I left these to 100. And we just adjusted this one and made it, now it's 154 grams. And so this will be the equilibrium of these two, or you could say this one is the equilibrium of these two, or this is the equilibrium of these two. They're all equilibriums of each other. And that's why it doesn't really matter which one we choose. All right, so now we're going to set up to do another trial. For our third and final trial, this time I put the one at 0, one at 160, and one at 240, so they're not symmetrical. So this is not going to be as easy. It's going to take a little more effort. So starting with 100 on each one, I'm going to have to put on some masses. I'm going to turn this so you maybe can see it. And it's going to take me a little bit to play with it to get it to balance. So here we go.
So I'm putting on a 50 over here, and let's put another 50 over here. So if I need to put a lot more, so maybe let's just for fun put this is a 200. And let's put a 200 over here. So I'm going to take off this one and put on, this is a 20. So let's take off the 50 here and put on a 20 over here. Let's put another 20 over here. Boy, I'm going to need a 50. Let's put a 10 over here. Another 10. 10's too much. Alright. Let's put a 5. So let's put a 20, 40. Let's see. This is a 5. Let's put a 2 on top of that. And another 2 on that. How are we doing? Still want to go this way a little bit. Might be able to put, let's put a 20 on that is going to be too much. Yep. Put a 10 on there. Getting close, getting close.
Okay, we're going to call that pretty close. I'm going to pause here and count up the weights here. First of all, directions are at 0, 160, and 240. And our 0 is at 200 and 200, 300, and 320, 30, 330, 2, 4, 6, 7, 12, 12 plus 200 and 300, so that's 330, 120, 30 plus 12, so it's 342, so that's 342. This one is 100 to 305, 305, and this one is 5, 6, 7, 8, 9, 10, 11, 12. So that would be 112. All right. So those are our masses in grams for our third trial. Okay, once you have your data, then it becomes follow the directions. And really, you can do it all on your own, but I'm just going to go ahead and do a quick little example here. So we're going to begin by drawing a large XY axis in your lab book. This is not the lab book, this is a piece of paper just for showing you. Then you're going to draw the 3 vectors from the center of your paper using a scale where the length of the vector will correspond to its weight. For example, if you have 200 grams, maybe you can use a 10 centimeter line. So that would be 20 grams per centimeter. So for our first one, we have 100 grams. So I'm going to use 10 grams per centimeter. So our first vector, I'm going to go along the 0 degrees and make a mark here at 10 centimeters. And that's going to be our first vector. Okay, first vector is there. A little hard to see because it's right on the x-axis. Now the next one is at 240 degrees. 120 degrees. So to do 120 degrees, we do what you've learned to do long ago, and we're going to use the protractor. And we're going to go 120, make a mark. And since we used 100 for our mass, we're going to use so our scale is 1 centimeter equals 10 grams. All right, that's our scale. Now, you can have a different scale on each drawing depending on what you choose. So the next one was at 240, or I could go upside down here at 120. And make another vector here going 10 centimeters. And now I have the 3 vectors. I'm going to label this one F1, this one F2, and you'll see this here in the drawing here. And this one is going to be our equilibriant. I could choose any one of these 3 to be exactly the same thing because it doesn't really matter. All right, we'll pause there. So to add vectors, we need to have them nose to tail. So we're going to take this vector here, the F1. It's the easiest one because it's on the horizontal. In your lab books, you'll have lines. Perhaps if you have one, you can take, you know it's 10 centimeters, so you're going to move this up to here. And we're going to go all the way up to 10 centimeters, and that's going to be our F1 as well. But we just took it and moved it here so it's nose to tail. So now we're going to draw what our resultant vector would be, and that's what this drawing here is trying to show you. So we moved it up to here, and now we're going to draw our resultant vector. So let's choose another color for that. And we're going to draw from there back to the origin. And so that's our resultant vector. Now, it is what's going to be written right here. So the first thing I need to do is measure the magnitude of that. You say it should be 100. Yeah, it should be 100, but my drawing or my weights might have been off a little bit. So I actually get 9.8 centimeters or so. So then that would be, I get a magnitude of 98 grams. And my direction would be taking my protractor, and I'm going to measure it, and it's right there at 60 degrees. So that's going to be 60 degrees. My graphical, equilibrium graphical is what it must equal. So that's what's on the other side. Now, we have the equilibrium observed. That's what we drew. Now we're going to draw this guy exactly on the opposite side. So I'm going to go from 0, and actually I'm going to go, just so I can line it up, I'm going to line it up exactly with this vector, and you will see that my drawing is just a little bit off, just a tiny bit. And that's okay, because in science we sometimes have our measurements off a little bit. And that's what this graph is trying to show you, that there's two possible. There's first of all the one we drew and when we had our magnitude of our equilibrium. Now we're going to do one equilibrium graphical. And so this one, the equilibrium graphical, will be the same magnitude. And now we need to figure out the degrees. It's going to be around 240. So let's check it. So I have it at about 239 degrees. All right. Now we're going to do resultant calculated. To do resultant calculated, we're going to need to use the law of cosines and the law of sines here to calculate it. All the instructions for doing that are right back here. You can follow it step by step. The diagram here helps you know which angles are A and C and so forth. So here's an example of one student's lab book. They showed their work for their resultant calculated. That number is going to go into your data table, and then that's going to be the magnitude, and that's, remember, your scale. So then you need to report back not just the scale, but the actual magnitude of it, and then also the angle. Figure out what the angle is for your resultant resultant calculated. So that's what's going to go in here. So then you get to repeat this process for this trial and this trial, and then you'll be done with your data table and your drawings for this part of the lab. Then we're going to go on and take a look at some of the questions. Okay, let's take a look at some of the questions. First question is, could all three pulleys be placed in the same two adjacent quadrants and the forces adjusted to produce equilibrium? Well, adjacent quadrants would mean here's a quadrant and here's a quadrant. Here's a quadrant and here's a quadrant. Could we be in two adjacent quadrants? So that would mean this would have to be past the 180, and this would have to be past the 0, so that they're all in one half of the thing. Is there a way that we could adjust this so that we can find equilibrium. So I set it up. I'm going to let you answer the question. Now, what would be the position of two forces relative to each other when the resultant has a maximum value? So if you wanted the biggest resultant, how would you get the maximum value? Well, if you had two people pulling against a third person, what would be the best position to have them in? So you see, if two people, the closer two people can come together to pull, the more force there will be against this resultant. The further apart these guys go, the less they are pulling in this direction against the resultant. So I'll let you answer those questions as well, based on what I just showed you. Now, what if the force table was not level? And then what factors may have contributed to inaccurate results? This is the one I want you to think about. What would make it so that we didn't get the right results? I'll let you answer that, but I'm going to try to show you what would happen if the force table was not level. Okay, the question is, what about if the table is not level? Well, first, we're going to notice that that ring is in the middle and that the table is level. Then I'm going to put one leg up and we'll see if it still has the ring in the middle. Okay, so now you can see that the table is up on one leg. So let's go see if the ring is still in the middle or not. You can see the ring is still in the middle. So does it matter if it's leveled? And maybe you can put in there, why do you think it doesn't matter if it is leveled? Think about the weights. Okay, that's it for our lab. Remember to write a conclusion, and you should include some of the things that you learned or demonstrated by this lab. And please write your lab in the correct order.